I'm a huge believer in embodied cognition, that we learn by moving our bodies and moving objects with gestures and intent. So we have some research here. I won't read over it for you. But appropriate sensory motor experiences are necessary for human cognition to develop at the highest level. This is all fairly recent research. There's a lot of cognitive science at the moment, but we're being sold the declarative knowledge, the arrow pointing there, and it's all about long-term memory and getting things into there. However, declarative knowledge is not a list of facts. This is Professor Camilla Gilmore fairly recently. It's a network of associations, and there are lots of different ways that we build up that knowledge. And this is another part of that talk on working memory, but it's about longer term learning and long-term memory, and meaning comes from making connection to existing knowledge and understanding or experiences. And this is very much tied into some of Clemens and Sarama's, but we need to be doing things as well, not just learning facts off by heart. We need to build experiences. So when using manipulatives, it's quite complex, and you have to be very careful and think about what you're doing. You can't just grab a piece of manipulative and thinking that's going to be good. There's a saying there, blocks is blocks and numbers is numbers, and it's our job to make those connections, and some of the materials don't do that very, very well, and they're probably not a great choice. So epistemic fidelity is the strength and breadth of the analogical mapping of the physical material to the mathematical domain. How well does it link to it? Transparency is how the apparatus reflects and embodies mathematical structure. And it must be transparent to the user, it must be obvious to the user, and it doesn't have to be a whole new thing you have to learn just to make that connection. Affordance is what's something you can do with something, what it offers to you. So for example, double-sided counters or two-color counters revolutionized my teaching in terms of the subtraction concept of not. So you've got a load of yellow ones, turn the red ones over, not those, that's subtraction. Use them for positives and negatives. They offer a lot. They're very simple, but they bring a lot to the teaching. Gesture, very important gesture, but when we're doing manipulatives, whether they're real or virtual, there are gestures. For example, if they're virtual, we may select all of it, we lasso it. And that's an intention, a gesture that reflects the fact that we know we need to grab all of it, and it relates, as we'll see, to the distributive law. But it's also important that the teacher's language matches the gestures. So one of my favourite bête noirs is the 100 square that starts at the top and comes down. So as the number gets bigger, you're coming down there. So my hand's coming down when I'm demonstrating. So I use the reverse one so that as I count numbers up, you will see us going up. So gesture is important. It has to match. The language must match the gesture going with the concept. And concreteness fading is that probably people say, well, the apps are doing it for them. No, the apps are not the way of doing maths. The apps are the way of explaining the mathematical concept and getting the child to understand how this works. So eventually you must leave the app behind. However, in intervention, I will often bring the app back and I use the visuals alongside there. But basically, you're aiming to get to the abstract. The app is not the way of doing the maths. It's a way of getting to understand and comprehend the maths. A lot of talk about whether you should use apps with any very young children. I kind of disagree. So there's this one on using manipulatives to students at risk or a disability. And their findings are very different. They were consistent across the age. It's not just for the young children. So regardless of student age. And not only does it help the concept, but it also helps develop students' mathematical processes. And then we come to the idea of what's concrete. Concrete things are okay, and they're very important at the beginning, but they soon become clumsy, and you need too many of them. And so, for example, in base 10, the idea is that we put 10 ones into the box and exchange that and bring out one 10 stick isn't really the concept. The concept of unitizing is you put those 10 ones together to form one 10 stick, and an animation such as that, and then what we're going to look at, can do that. So we can have what we call integrated concrete. which is how the abstractions and the mathematical rules, if you like, are connected to some physical activity or some virtual or real manipulative that we used. So it's much more integrated and a much deeper understanding. So these are some of the apps that are very quick guided tour of some of the things I'm going to use. So at the primary end of things, we have Math Learning Center, loads of different things here. And for example, they've got the number frames. They have an open web app, an iOS and Chrome. So if we open this one here, now one of the reasons I like this one is, and I use this as well, is because when I've set up a certain activity, I can then save that as a link, put that into my planning, and I can also, if I'm using this program and the children have got the app, you can just show that display code and they put that in. There are other ways around that, using QR codes as well, we'll look at later. Desmos is massive, and if you haven't had a look at that, do go and have a look. These are just tasters, so you've got all those tools there. You've got Desmos Classroom as well, phenomenal. If you haven't looked, do. PhET, everybody thinks it's about science, but actually I've chosen maths here, which is showing on there, and I've got a whole load of really wonderful things there I use quite a lot. And if I've got one, I can just choose something simple here, say this one here. Then I go to it, I've got an app, I've got about it, I've got teaching resources, I've got activities, and a few different language translations. So again, go and have a look. I just encourage you to try it out. Biznos is, I don't think it's very well known. It's great for demos and investigation and exploration. One of my favorites, the Number Explorer. You can look at numbers as triangles, squares. You can look at divisibility rules, factor pairs. I'd use that more in investigative, exploring, guided exploration. GeoGebra Maths resources, massive there. I haven't got time to go into all those, but you see they've got a huge number of resources. Have a go and have a play, go and have a look. MathSpot, I'm sure everybody's familiar with. I'm not using that much today because I won't have time to set each one up, so I've used ones where I can set it up and use the share code. But as well as manipulatives, there's a whole range of things here, and it does it all for free, although you can now get MathSpot membership, very reasonable price. So go and have a look at that. It's just so much on there. And what I will be using today a lot is, it was called the Mathigon Polypad, and the night before I had the technical run through, I got an email at 1 minute to midnight telling me it all changed. Hence panic over the next morning, and it's now called Amplify. It's all teamed up with other things. Very exciting. And this one here, I can do lots of things, but I can also draw on it, and when I want to, I can give my pad I've designed a name, save it, and then I can change the share that code with students. So that I'll be using a lot today because I've been able to set things up in advance to save time. So let's start with number, and this is Polypad, Dean Space 10, and it's the same as the physical one, but you can actually, you don't have to exchange, you can merge them or you can split them. So you'll see 10 there, you can merge that or split them. What I like about the splitting there is they actually separate out. Some of them they don't, so you do get the composition and the decomposition, the composing and decomposing. There you can merge those, and then you can do things like grab all of those and merge those. And it's a much faster way of showing things, and it also means that you can go to much larger numbers, as we'll see in a moment. This is Brainy Camp. It's not free. This costs money, but I just want to show you what things can look like. So there we go. So we've got this. You can size this up and change it. You can change all the number of columns. But suppose you want to do division, and we want to do 42. So we've got 4 tens. The best you can do is to have 1 10 in each. That leaves your 10 still to be shared out. So we are going to break that up, decompose it, and we now have got 12. So we can have 3 4s. We could get 4 into each group, 4 1s into each group, and share those out. There's various versions of this on different websites. And the beauty of this is, what I like is you can write on this as well, so you can then show, okay, so I was doing, now what I'm actually going to do is to unlock that, move that out of the way for the moment, and I'm going to show the original question, which was 42 divided by 3, and then connect that to what I did. So you've got 4 ones, the best you can do is 4 tens, the best you can do is 1 10 in each, but that leaves you with 1 10 left over, which you then decompose or rename or regroup or break down into 12 ones. Then the best we can do is 4 ones in each, so we end up with 1 10 and 4 ones in each group. So if we go back to our board now, so this is MathSpot. There's loads of things, but after I did a webinar recently, or quite a while ago now I guess, Johnny put this together. It's the only website I know that does this. So let's just have 3 columns, and we'll have a table with numerals, and let's suppose that we have 20. Now there's a button up here, if it's in that position you can just quickly copy across, so that's fast. There we go. So what we're going to do is lasso the whole thing, and it's when you multiply by 10 you add a 0 on the end, as they say. So why is that? Because this is really scaling, where you change the size of the counter unit. So the tens have become hundreds and the ones have become tens, so everything needs to shimmy across here. And so we get 320, and now if we grab all of these we can divide those by 10, and now what I'm going to do is to change that so that the group that I've lassoed, I can control that with my arrow keys on my keyboard. And so that's the knock the 0 off the end idea. So that's the only app I know currently that does that. Thanks to Johnny for putting that one together. Amplified polypads, using number cards. Here we go, and we're in. So we'll leave the 2.5 million for the moment. So I'm going to go to the number ones, and I'm going to get number cards. I just take a number like 25, and there are various controls you can use here. You can, to zoom in you can use these, and to move things around you can use that. But I'm using keyboard shortcuts, which if you practice those are all a combination of using Control, Option, Command or spacebar on the Mac, and it's fairly similar on the Windows. So you can split those, and you've then got that, and then you can split that into 2 tens, and you can split this into 5 ones, and then you can recombine or merge or compose just those, or you can merge those, and then you could merge them all together, or you could split them and then split everything again, and then just grab the whole thing and merge it. And the beauty is that you can make incredibly large numbers like 2.5 million, usually normally one out the range of what you can do with physical apps, but here you can experiment and explore. So if you split that one up, we've got 2 million, let's leave that out of the way. We've got 500,000, let's split that. What's that look like? Well, it's 500,000s. And what about if we split that lot up? What does that look like? Oh, now we're running out of space, so I'm going to zoom out using my wheel on my mouse, so you can use this over here. Okay, that's great. So suppose we split all that up. What does that look like? No, not that one. I want to split that one. So select it, lasso it, all of it. Let's split that up. Whoa, now we're really running out of space here. So let's get back into somewhere else. Get this out of the way. Let's roll that up there. Now, what have we got if we merge that down, split that down? And then you get that, and so it goes on. And you can go well outside the range you can normally do, and let children explore and play around, and then generalize and conjecture. So this is MathSpot first of all. If you want to do, after you use Dean's blocks, you then use place value counters, which are far more abstract. So let's suppose we're going to hundreds, and we want to show a table with numerals. And you can zoom in and out of this, making things bigger or smaller. So suppose we wanted to do the same one, which was 42. Now you'll notice this one is still on this one, so I do 2, 3, 4. Not quite in my place value there. 42, and I want to divide that by 3, so you get 110 in each of your groups. Now what I can't do here is draw lines across here, so I'm spreading them well out. That leaves me the 10 ones there, which I'll have to put over there. Let's exchange those. So now I've got 12 ones, so that means 3 in each group here, and probably it's just as well to pick them off. Oh no, 3 groups. Well, there you go. 3 threes are only 9, so actually we could do 3 fours. And when children first of all share, they share out in ones, then they start sharing out in twos, and they eventually learn their tables and they know exactly what's going to be in there because they're doing division as the inverse of multiplication. So 3 times what? Or what number 3 times? And here we are doing the same sort of thing in Polypad, which I can just shift this down a little bit, zoom in a little bit, not too much. So I find the keyboard shortcuts really handy. So here you've got 1, 10 in each, and I've got a bit more room to play with this app up here. It's not so tight on space. Split those up. Now what I like to do is to change the colour of those so they look like the ones. They're actually all ones, they are split up. So I had now, what was that? Ooh, 18 of those, was it? 2, 4, 5, 3, 8, so 3, 6 in each, so I can grab 5 to start with, and another 3 in here, and another 3 in here, makes 6, and I've got 5 and then 1 in there. So there's different ways that children will decide to regroup and move them around. And also with this one I can show, I forgot to change the colour, I started off with 4 10s and 8 1s, so 3 times 1 10 is the best in each. I have 1 10 left over, which I break into 10 1s, and I get 6. So that's all that. You can share all of these by saving them. I save all of mine. I'm not going to show you those, I've got some names of pupils on them. So back to here. This is Amplify Polypad, and the multiplication area model I think is very underused, and it forms a beautiful link from numbers and learning how to do multiplication and other things onto algebra and multiplying out binomials and factorizing. So let's have a look at that. Again, these are all boards that I've prepared in advance. So one of the things I like about this is if we are multiplying 3 10s by 2 10s, which in algebra becomes 3x by 2x, we'll notice that each square is 10 by 10, 100, and we have 6 of them because there are 3 along here and 2 along there. But going back to more basic simple mathematics, suppose we wanted to do 13 multiplied by 12. So you've got 10 and 3 there and there. This is exactly like if you're teaching secondary, what the algebra is going to look like. And you have, so the 13 has become 10 and 3, and the 12 has become 10 and 2 here. And the area of this bit here is 10 times 10, or 10 squared. Here we have 10 multiplied by 3, which is 30. And here we have 2 multiplied by 10, which is 20. And over here we have 2 multiplied by 3 is 6. So if we're doing 13 times 12, one of the ways we can introduce this is if you start down here, you could do 2 3s are 6, and 2 10s are 20, and 10 3s or 3 10s are 30, and 10 10s are 100. So you've there got 4 regions, which in algebra these two will be the key. And then what I want to do is get rid of all of that. You've got the backspace here, you can do lots of things. You can go forwards and backwards, even with prepared things. Let's go forward where we were there. And you can also start to look at this as being 13 times 10 and times 2. So you can break it up in not 4 regions, but 2 regions. You have your 13 multiplied by 10 and your 13 multiplied by 2. So if we get 13 times 12, we do 13 times by 10, which is 130, and we do 30 multiplied by 2. Or you can put those up the other way. So you're going into 4 regions. You're also doing lots of things which are leading onto FOIL and distributed law, because you're doing 10 by 3 and 10 plus 2, and we'll look at that on another app which is all set up to do that. So this is PhET, which people think is for maths, but it's also physics, but it's also for maths. So if we have a look at this one here, you have first of all 10 by 10, but you can make that bigger by changing them either here or by dragging these there as well. So let's take our same example, which is 13 multiplied by 12, and we can decide how we break these up. So we can break this one up here after 10, so we've got a 10 there, and also break this one up here, so we've got a 10 there. And instead of doing it like that, you can in fact have them like this, which are like the Dean's blocks, also coming later with the algebra tiles. And you can break this up into different ways, so you can look at it as being 100 there, 30 there, and 20, or you can look at the factors of each one, 10 times 10, 10 times 3, 10 times 30, and you can also look at the multiplication here, how it's being done. So we're having 10 times 10, 10 times 3, which is the distributive law, and then 2 times 10 and 2 times 3. They don't have to know those names, but these ideas are very useful later on for secondary maths and algebra. And you can of course go up to 20 by 20, and you can go up to 100 by 100. So that's a great way of tying up a lot of different aspects of beginnings of algebra as well as arithmetic. So this is Polypad again, and I love these. Been using these a lot the last couple of years. So we have prime numbers here. 1 is not a prime, it's greyed out. 2 is a prime. It has only one prime factor, 2. It has another factor, 1 as well. So these numbers, we can see they're prime factors. Now if you take the number 4, one of the factors is of course 1, but you won't see that here, we're only looking at prime. You can see it's made up of the product of 2 primes, so we can split that up. That makes 4 a square number because we can have something times itself. 6 is the product of 2 primes, 2 different primes. 8 is actually a cube number, a perfect cube, because it is the product of 3 primes, so we can split it up into a number times itself, or a number cubed. So what I find interesting to watch with older pupils is they're looking at the number of each colour, the number of each prime factor, before they even do it. So the number 12, we can see that it's got 2 factors, prime factors which are the same, and 1 which is different. So you can play around with lots of things there. I use it a lot for, Johnny actually put a video up the other day exactly the same way as I do this. So people use Venn diagrams for HF and LCM. I'm not a huge fan. So I'm going down to the number and the prime factor circles, and I'm going to make myself a number 24 here and bring that out. And I'm also going to make a 36. I can of course have all this board was prepared, but I chose not to put this on here so I could show you how I do it. Now we can see the 24 has got 3 prime factors which are the same. That's 2 cubed, or 2 times 2 times 2, and another one there. Let's just move those. I like this as you can lasso and move them around really quickly as well. So we've got 36 there. Now what I tend to do is what's called the line-up method, is I line these things up underneath each other so I can see what's common and what's not. It's quite a standard way of doing things, but not Venn diagrams, because I think Venn diagrams hide a lot of what's going on. So what's the highest common factor? Well, common means it's the same in both. So we can see that we've got a 2 here is a common prime factor, and there's also another 2, and we notice that we've got 1, 3 that's common as well. So there are various factors here. 1 is always a factor. We probably ought to think about it, but it's not a prime factor. But we also have 2, 3, 2 times 2 is 4, 2 times 3 is 6, and 4 times 3 is 12. So it's actually 12. So common factors, well, 1 is everywhere, but 2 and another 2, that's 4, and another 3, that's 12. So the highest common factor is 12. And if we have a look here, can we see the 12 in here? Yes, it's here. And can we see the 12 in here? Yes, it's here. So you can also see that here it's 12 multiplied by 2, and here you can see this number here is 12 multiplied by 3. Now what about the lowest common multiple? Again, let's keep that out of the way. So what I'm going to do is make a copy of the largest number and say, okay, is this a multiple of 36? Well, clearly it's 1 times 36, but is it also a multiple of 24? And we haven't quite got it because we've got the 2. You can see a 2, 2 and 3 in here, but we need another 2. So what we're going to do is do that. Now, is this a multiple of 24? Can we see this in here? Yes. And what's it multiplied by? An extra 3, so it's 3 times 24. Is it a multiple of 36? Can you see the 36 in here? Yes, it's here and here. It's actually 2 times 36, and this number turns out to be 72. So without Venn diagrams, and of course that works for 3, 4, 5, 6, any numbers you like, whereas Venn diagrams really struggle beyond 2 numbers. And the last sort of area of this one is doing squares and square roots. Now, one of the things I've noticed students doing is they're counting the number of each colour, not just the number. So I can tell you already this is a square number. This has a perfect square root because I'm able to break it into a number times itself. And the reason I realise I can do that is there are 4 orange ones here, so I can have 2 orange ones in here and 2 orange ones in here, remembering all the time that we'll be finding the product of these numbers, they're not addition, and then 1, 3 in there and 1, 3 in there. And students actually get very quickly to the fact that if you're going to find the square root of a number, if it's a perfect square, it will have an even number of each prime factor. In other words, the exponents or powers need to be even. So we get there 12. And similarly that expands for perfect cubes. They must be, the number of each must be divisible by 3. Fractions, lots of different things you can do here. First of all, equivalence. So first of all, this is Mathicon, and I've prepared this board already. I go here, you'll see that it's got a name and it's got a polypad link I can share here, but let's keep that out of the way for the moment, and we'll have our fractions ready just in case we want to do something. So we got fraction bars and fraction circles. So first of all, equivalence. Well, what I did here to show 2/3 was I got 2/3. I could chop it off like that, or I can leave the thirds there and show you this. Now, again, this is going to be done by the app, but then we're leading to what's going on, what happens. If I do this, I'm going to double the number of parts, and each one will be half the size. So I'm now going to have 4, 6. And if I do this and go this, I've now got 3 times the number of parts, so each one's 1/3 of the size. And these are all equivalent fractions. They're all equal to 2/3, but they're using smaller and smaller parts to do it. So that's another way. Another way I can show 3/5 is to just chop the end off here and just have 3/5. And again, I can do the same thing here and keep adding all those and show that they're all the same length, but they're different ways. The more parts you have, the smaller each one is. Fraction, decimal, percent. So again, this is one I've set up already. So I've got this here, and now here I split them there, and I've changed the markers so they're percent. I've got fractions or percent or decimal, so I'll leave them as percent. This one here, I've done the whole and I've changed them all to decimal. This one here, what I did was I actually split them up. So if you merge them, what I did was to split them up, and then to choose the first one to have as fractions, the second one to have as percent, the next one to have as decimals, and then you can carry on like that. So that's how you can easily connect fraction, decimal, percentage. And then the last one, I didn't show, no, it's coming later on. You can also do these as well. You can join those together I'll come back to those in a minute, more for mixed numbers. Fraction decimal percent again. This is on Visnos, and it's one of my favourites. So you get a 100 square here, which is commonly used to do them, and you can decide how many groups you want. You can have 10 like this, so that if you did that, for example, then the orange would be 3/10 of the whole thing, and it would be white would be 7/10. The orange would be 30%, and that would be that. You can also change it all to 100 is what I probably use more commonly. So if we do that this time, we get that, and we can have them as decimal. So that's a wonderful way of doing that. You can have more than 2 colours, you can have 3 colours, you can have sections, you can randomise it, you know, go and have a play. But that is a very powerful way of what I normally do with 100 squares on paper anyway. This is much faster doing this, and it's easy for me to demonstrate and quicker for them to understand. Again, back to Polypad, and this time I'm going to use fraction circles. So these are wholes, so I've got 1 3/8, so I've got 8/8 of the whole, and so I only want 3/8 there, and I only want 5/6. Again, this is going to be done automatically, but I'm not using the app to do it. This is to talk about it and to get the children to explain what happened, and then to slowly concrete fading, leaving this behind, but coming back to it whenever I need to. So I've got 1 3/8 and 2 5/6, so it's easy to add the whole numbers together, that's 3. Now I want to add these together, but they're different types. So what happens if I try and merge those? Well, not really an option. Can I make the 8ths? If I double the numerator and denominator, I'll get 16ths. I can't change 6 into 16ths. 24ths I can, because 6 goes into 24. So I need to double top times 3 times 4 gives me that. And I can split these off and drag them over one by one. Or if I go back there, I put them, yep, just for a little bit of magic. If you slow this down, you can't do this. I did video it and slow them down. You'll see that happening. And then can I simplify that? I'm going the other way now. No, nothing happening. Can I simplify this? Oh yes, 15, 15, 12, 12, 8, 8, all the way down to one whole. So I've got that there. Okay, so although I'm using the app to do it at first, I'm actually working alongside that and trying to remove the app concreteness fading. Then we've got multiplying and dividing with fractions, skip verification, and this is scalar multiplication, so 1/4 times 3 or 3 times 1/4 is, now I'm going to use my option, I drag it, let go with my mouse, drag it, let go with my mouse. So you can use copy down. I like that because I put things exactly where I want them as I go. 3/4 times 3 is 3/4, and then I'm going to do 1, 2, 3. A half divided by 6 means I want to split that half into 6 equal pieces. So 2, 3, 4, 5, 6 equal pieces. So each one is a 1/12. And of course, if you have 6 lots of a 1/12, you get 6/12, which is indeed a half. 6 divided by half is asking the question, how many halves are there in 6 holes? Well, there are 2 halves in every hole. So if I break these down into halves, I will get 6 times 2, which is 12. And that's the beginning of the Kentucky Fried Chicken, whatever it's called. I don't know what it's called because I never use it. I wouldn't dream of it. I use diagrams like this to get children to, pupils to get towards the abstraction. That's all the fraction stuff. Apart from the area model, this is quite slow. Not everybody understands it, but I'm just going to show you this anyway. This is off FET. Is it really FET? No, PBS Learning Media. I've got the wrong heading on that. Did so many of these. Right, so start. So we'll start with something very simple, like a half times the third, which means a half of a third. So I've got this third here, but I only want a half of it. So one way is to drag this over on there, and you get this. So what have we got there? We've got 1 out of 6. So I change the grid there. It becomes more obvious it's 1 out of 6. Let's reset that and do something more interesting. So example, 2/3 times 3/4, whether, if you know about cancelling, there's going to be obviously a lot of cancelling, and this shows this very nicely. So we're going to break this 3/4 here. We're going to get 2/3 of it. So here we had our 3/4. Now we've only got 2/3 of it, and it's not so obvious there. If you change the grid, it still doesn't really show it. But if you do this, you can see, if you do that, it has actually become 1 out of 2. So it also leads to the cancelling. Again, the app is being used to develop in the abstract, leaving this behind. So algebra. Here we go. So a lot of things, some of this might be new to you if you're not familiar with the concept of zero pairs. So let's have a look anyway. So collecting visual representation. So we are again in Mathscon because I've set it up. Now I'm just going to scroll that down a little bit and zoom in a little bit, but not too much. So collecting like terms and zero pairs. So we have some students in secondary particularly who struggle with things like x plus x squared is x cubed, etc. What I like about this is that each variable has a shape, so squares are squares, because you run out of luck beyond 2 dimensions, by which time though the ideas have already been fixed in. Just going to zoom out a little bit more so I get all of those in. I think we've got everything now. There we go. Okay, so an x is an area model. It measures 1 unit across by x there, and this is y along by 1. So the R area model, there must always be 1. And this is an x squared measuring x by x. This is an xy measuring x along there, and if I were to rotate it, you can see that it's y along there. So just take that back to where I was. And then we have the idea of zero pairs. So if you have an x and a negative x, they're called additive inverses or zero pairs or opposites, and together they make 0, which I can then cover, and I'm doing backspace on my keyboard to get rid of those. So if we put 4 x's and 3 negative x's, you can put them one at a time, or you can do things like this. In some apps it just disappears straight away. In this one they leave a ghost, they leave a 0 there so you can see what's happened and then get rid of it, get it out of the way. So similarly, if we put a negative xy with an xy, even though they weren't lined up for shape, they have done that. And of course you can add x squareds to x squareds, and you can add x's to x's. So it's an idea of collecting like terms but also zero pairs. Additive inverses. Add or subtract, so we'll go back, we'll be on the same page but move further down. So the simple addition is easy, but there is another idea which is to do with subtraction, and it's adding the additive inverse. So students will first of all have had to work with positive and negative integers and be really confident before doing this. So when we come to subtraction, it's very easy. If you wanted to add 3x and x, it would be 4x. But subtraction, how can you subtract 2x? Well, one of those is the take away model, so you take it away and delete it, get rid of it. But that doesn't make a whole lot of sense when we come to 2x minus 4x. So the other way that we can subtract 2x's here is to go to our algebra tiles and get the additive inverse, the negative, the opposite. So instead of subtracting 2x's, we're going to add the opposite. This will have the same effect because it will get rid of, if you like, those 2x's there. So instead of subtracting, taking away, which has a limited lifespan when you're working in algebra, you add the negative, you add the additive inverse. So if I want to do 2x minus 4x, the taking away model is finished. But what I can do is to get 4 negative x's, and I'm doing a shortcut here, which is to hold and release. I'm holding down Option and then release with my mouse. And I'll do this one at a time because it's more obvious. That's a 0 pair there, and then there's another 0 pair there. And then we'll make that. If I go back to where we started that, what I can do is probably just plonk those on top of those and do that. So you do it one by one to start with, and as the pupils become more confident, you then use much faster methods. So that's subtraction as the addition of the additive inverse. Again, it will only work with like terms. Again, polypad, and this time we look at scalar multiplication, additive inverse, and subtraction as addition of negative. So first of all, scalar multiplication, which means, right, a couple of things. These are my own weird sort of kind of ways of doing things. When things are in brackets, then I will stick them together. So 2x plus 4y, because it's in brackets, it stands for one thing, so I stick them together rather than separate them. And here's the example of a gesture. So I'm going to do multiply by 3, I'm going to grab it all. So this reminds the students and develops the concept that we drag all of it. Again, I'm going to use some Option on my keyboard here, release, Option there. And what I tend to do is once I've taken them outside of the brackets, then I separate them out. And then you can add these together. So you've got 3 lots of 4y is 12y, and you've got 6x there. If you have a negative in front, that is basically negating. So again, I grab all of it, and I'm then going to negate it all. And then again, I do, because I'm taking outside of brackets, I personally like to do that. So again, by grabbing it all, you're emphasizing the fact that both parts are multiplied, and here you negate both parts. If you only do this in abstract, often the second one, you'll get 6x plus 4y, you'll get negative x plus 4y. And this helps to emphasize this. To multiply by negative 3, we are going to scale it times 3, but also negate it, or negate it and scale it. So I can first of all scale this times 3, and then grab all of it and negate it. And then what I would personally do is to separate those out and start putting all those together. You can put them all in a straight line, arrange them any way you like, as long as they kind of form a group. So again, it was the multiplication on both. Or if we just backtrack that, I can first of all negate it and then scale it times 3 and then separate them and do all of that. Okay, if I come down here, now this is, again, you can't do subtraction as in taking away, so I'm going to interpret this as 2 of these, and then I'm going to add the opposite of that, 3 of the opposites of that. So subtraction becomes adding the opposite. So first of all, we have grab everything there and double it. And then here we're going to grab everything here, and in order to, well, let's do it now in order. Let's first of all multiply by 3. Then how do we subtract it? We do that by adding the opposites, so then we negate it all. And the grabbing all, this really key, I think, to this way of teaching, is that they get that it's everything here that's doubled, and everything here gets trebled, but also everything gets negated, and it's that gesture of lassoing that does this for us. And then we can start to put those together and get rid of all of that, and then do that. I won't do all of this because I'm going to run out of time otherwise. I don't think there's anything else on there. Okay, so if we go back to the PowerPoint there, so we've covered that scalar multiplication, just grabbing the whole thing and repeating it as many times. Additive inverse was the thing that when you add it is the opposite, and subtraction here you can't really take away anymore, so you're treating this as 2 of those and the negative of 3 lots of those. This is MathsBot, and this is something new, and I absolutely love this. It's changed my teaching and my pupils' understanding of multiplication. So this is a prime factor task, but he's added in this. So I'm going to use, remember this button up here, so I'm going to use my arrow keys. So I can do x times x times x, and I can either do it one at a time, like this, or I could grab the whole thing and say multiply it. And then of course I can do that. Why was that? Well, if I decompose it, so I click on it, decompose that, you can see it was actually x times x times x times x times x times x. So if you want to do, yeah, you can play around with that. Let's just tidy that, get rid of it. Suppose you want to do 3x times x. Well, 3x is this. Let's make it 3x times 2x. You can just grab it and say, okay, can you multiply all of that for me? Or if we break it up into what it was 2 times x times 3 times x. But to realise that 2x, as well as being x plus x, is also 2 times x, and that 3x, as well as being x plus x is 3 times x, then when we multiply these, basically we are going to do the 2 times 3 and the x times x, and then multiply those. So we're going to do this, and then if I tidy that up, we can start developing laws of indices. And you could just grab all of that and do it all together, or you can do this as, you could multiply this part, x to the 4, but if you multiply all of that, you're going to get x to the 6. And why is that? Well, because we had x to the 4 over here, which is 4x's in a chain multiplied, and x squared over there, so I didn't grab it, x squared over there, which is 2x's. So if we put them in a chain, you're going to get 6x's multiplied together, or x to the 6. That's a lovely way, and he's also just adding negatives in it as well. The other day I was going to mention that. If I got a tile of -2, this is brand new, add a tile. So if I get a -2 and then multiply by -2, I'll get -4, and if I multiply that. I didn't show that at the conference because that wasn't out then as far as I know. And then we've got the area model, which isn't really used very much. Skip verification. Again, I'm in polypad because then I can set this all up in advance. So these are the 2 factors here, 2x times x, and it's space filling. What will fill there? Well, it's going to be an x squared. I'll just zoom in a little bit for you. And then all I'm going to do is to click on that with my option, drag, release, and then copy that lot, drag, release. So it means I can work at the board very fast, but I'm actually not at the board, I'd be sat at a computer. If we've got 2x times 3y, then what's going to go in here? An xy, which I may have to rotate. Yep. So I'm going to have to rotate that one around so that the sides match up, and then I can either click the copy button, or I'm holding down option and releasing my mouse for each copy, and then do that. So that's just simple multiplication of variables. It only works up to x squared, etc., but it's a good start. If you want to factorize, an example here, so here are our x's, so you could put the x squared and x squared like that, and as we'll see in a moment, that would give you a length of 2x plus 4 there and that there, but we could do a little bit better than that, and this is where you struggle to bring meaning to what it means to rearrange on here. If we do this, we will get a better factorized form of that, fully factorized. So the length of this is 2x, and the length of this is, ooh, wrong one. The length of the, oh, same again, wrong. Okay, let's grab on that. There we go. Less haste, more speed. I'll do that, and then I could just do that. Okay, so we've actually factorized that now into 2x time here is one factor, and the other is x plus 2 there. And if we move across to here, x squared plus 5x plus 6. I did mention earlier on that the key parts when we were doing number is the top right and the bottom right. So we can, the x squared goes like this. The 6 can be one row of 6, but if you do that, you're not going to fit in there. So then you try the other factor pair, which is 2 times 3, and then you'll discover that you can get 3 of those and put them in there. If we turn those round, we can do that. And then our factors are, we've got x plus 2 along there, and x plus 3 along there. So we factorize that into x plus 2 times x plus 3. And if you are doing this at secondary level, then you need to focus on the ways of arranging that, the factor pairs for that, and the ways of arranging that, and then try and make these fit. And sometimes you do have to bring in a negative, a zero pair in more complex examples. This is, I use a program called Graspable Maths. I pay a small amount per month to use it, both in my teaching and sharing links with my pupils. But this is a lovely collaboration between GeoGebra and Graspable Maths. And so when you get there, it's got some basic things for you to do here. And so here's an example of taking it through, a student through something. So I don't know why that's happened. I've got a fabulously fast internet connection. So what we're going to do here is close the equation here, and we're going to subtract 2 from both sides, or add negative 2 to both sides. That's the equation of doing that. You see that happening there. And if I click on that, it does that. This one I'll probably have to move it over to there. That was a valid step, but was it helpful? Yes, I thought it was. And we do this, and then you can click and drag, but I don't like teaching that, so I'm going to teach that I am going to divide both sides by 7. And it does that, but I don't really like that. So what I'm going to do instead is to do things as a fraction and put the equation over 7. I don't prefer the Vinken fraction bar. And then what we're going to do is to cancel it out and just get y. And it gives you some feedback. When it doesn't like things, it will go back and tell you and give you another go. So that's a really nice thing that's going on out there, and I haven't used that much yet, but I do use Graspable Maths a lot, but I know that a lot of secondary teachers really don't like it. I really do, and so do a lot of my pupils. Polypad stuff I think is phenomenal. One of the most recent things has been the function machines. So at a simple level, you x plus 1, you can also hide that as well if you want. You can show the expression or not. I'm going to actually show it here so you know what's going on. So you put a number in and it adds 1 to it, and out comes the other way. If I get rid of that and get myself another number card of 1. Well, the other thing I can do if I go down to algebra is, if I get my function machines, I can bring in a second one. And I can say, so you get a number in here, whatever number is x comes out here. And the confusing thing for young kids is that the x is the same as the x, so I used to use letters like a and b's. So if we just make this one 2x, in other words, get rid of the alphabet, double whatever number comes in. And so I use, with younger pupils, I use different numbers here. So if you do this, and then the 2 went in, the doubles comes out there. Other things you can do is you can take this and invert it. So 2x went in, you doubled it, now it came 4, so what was the other side? It was 2. And then you can do composite functions, or function by function, by putting 2 next to each other, and you can also tabulate them as well as to show what's happening as you put them in. And then you can haven't got time to do all of this, but I'll just do some of it quickly. You can then grab some axes and you can link that to there and do it. Then you can write down what you think is the equation here. If we just make that a little bit bigger. There's plenty of this on Mathigon's YouTube site, so you could try graphing that and seeing what, try changing this to fit. Loads of different things you can do. Go and watch the videos, and I put some on myself. So here's another little bit of setup to show you some stuff. We've got a table here. You can connect it to this to plot the points. You can maybe suggest you think the equation is y equals 3x plus 3, and then you can join that to there and say, oh, it's not quite right. So what I've done here is rather put numbers here, I've put sliders in, and I've adjusted them so they only go up in ones. So I can maybe try graphing that. That's y equals 2x plus 3, and move it up and down. So if you're doing y equals mx plus c, you're trying to get equations. Again, lots of stuff there.